Let's get into chapter 4, isomerism. Okay, those words won't mean anything just yet. Conformers and constitutional isomers. We'll start with the definition of an isomer. In order for two compounds to be isomers of one another, they have to have the same molecular formula. And the one that pops up in general chemistry for me is, let's see, C2H6O, I think. Right. So this can be made into CH3, CH2OH, the drinking kind, ethanol. Or it can be O, CH3, CH3. They got the same formula, but they're radically different structures. Now, this particular isomer is constitutional. And the reason for that is different connectivity. You have the same group of atoms, but they're connected differently. Right? The other type of isomer is stereoisomers. Stereoisomers have the same connectivity. This is different connectivity. If you have the same connectivity, then you have stereoisomers. Now when we get into stereoisomers, the conformers don't seem like they're significant, right? Because they're produced by the rotation around a single bond, around a sigma bond, right? So you say, well, who cares? They're spinning like this. How do you tell one isomer from the other? It's largely theoretical, right? Except we do have some experimental evidence because you can measure the energies required to go from one conformer to another. But the ones that are easier to rationalize are the ones that change the configuration. In other words, if you have, let's see, if we have say a carbon and we've got different groups attached to it, say we're going back with a hydrogen there and we're going back with a methyl here. And then we've coming out of the board with a bromine on this side and coming out of the board with a, I don't know, nitro on this side. Then if you swap places, say with this methyl and that bromine, now the methyl's coming out and the bromine's going back. That's a significant change in the configuration around that carbon. Okay. Maybe you want to get yourself a model kit, because we're going to need to build some models, I think. Yeah, just grab one. They should all be the same. I go as far as I can on the board, and then we'll switch to models when we have to. Now, when the configuration changes, say we have this one versus, let's see, we swapped places with these two, didn't we? So let's go like that. And let's put the methyl here and the bromine there, and we'll leave the nitro in its place. And hydrogen here. This configuration, this one compared to that one, they're not mirror images of each other. And think of your hands, right? You can't superimpose. If I say the back of my hand here and here, I can't superimpose my hands. They're mirror images of each other. If I draw a plane here, right, then it's the mirror image. If that's the case, then we have enantiomers. We don't have enantiomers here because we can't put this one out to the side here and flip it over and make it lay on itself. Right? Those are diastereomers. Enantiomer is mirror image, diastereomers not. But they do have different configurations. Okay, they're still connected to the same carbon. So the connectivity is the same. It's just that their positions are different. Okay. So we're trying to get through definitions at the moment. Maybe once we start to use them, it might make more sense. So I mentioned the conformers earlier. They just simply rotate around a single bond. And that's the first projection we're going to get to. I listed the projections that we're going to get to one at a time. First one, we've already been to the dash wedge. We know about that one. Then we're going to go to the Newman projection. And this one allows for rotation around a single bond. And that gives us different conformers. Okay, so that's the first topic we're gonna tackle is the Newman projection. It's coming up shortly. In fact, right now. So the Newman, excuse me. Yeah. I didn't look ahead on my hard copies to see which one was. I just knew that it was coming up next. I just didn't know how quick. I assume that Newman's somebody, some chemist somewhere who decided this was a good way to represent projections. But in order to, we can't do a Newman projection for this one because there's only one carbon. You need two carbons so that you have a single bond between them. And then we can draw the dash wedge projection like it's shown. Yeah, like it's shown in that slide. And then what you want to do is look at the spatial arrangement of the substituents on those carbons relative to one another. And Newman says the best way to do that is to rotate that dash wedge around like this so that you're looking down the axis of the sigma bond. Okay. And when you do that, the front carbon shows you actual connection points at the carbon for the substituents. And then the one in the back is given as a big circle. The way it's represented there, if you just take it in your mind and flip it like this, then you should see the Y's, actually it rotated the other direction, sorry, rotated this way. Then you see the Y's in the front and X's in the back. Like 6 of one, half dozen the other. I mean, it depends on your perspective. You can look at it either way, but you're looking down the axis of the carbon. Now, what can happen to give you different conformers is the rotation will put those front and back substituents in different relations to one another. And that's what we're going to define next. How are they arranged? If we look at that first one where there's, and notice that we have to do the Newman projection so that, let's see, they're going up here. They're going up like that, and they have to stagger off like this. So that's to the right, and then this one's going to be to the right, and then this one's going to be to the right. They have to stagger them slightly so that you can see them, but in reality, there's a 0 degree angle between the front and the back. We call that eclipsed, right? Because you can't see the one in the back. That's the problem with this method. If you can't see the one in the back, how are you going to represent it in a projection. So we have to offset it just a little bit, recognizing that it's really 0 degrees. Those are eclipsed. And this only works for sp3 hybridization. It doesn't work for anything else. Then if we rotate to the right a little more, we get into the 60-degree position. And that's, what is the word term for that? Excuse me. Staggered, excuse me. It's too obvious. So if we get to the one where we have a 60-degree, so we can represent these angles correctly. So we can do that one, and then we can do this one. And then in the front, we can do that, that, and that. So now this angle is 60 degrees. This is eclipsed, and this is staggered. Now, as they rotate, they go through a continuum of different angles. And there are energy values that can be assigned to each one of these positions, right? So that you can get a continuous curve. That's what we're going to show you in just a minute. But in order to go 360 degrees around, you've got to go through staggered eclipse, staggered eclipse, staggered eclipse until you get back to the 0 degree position. And that's what we're trying to show here with this representation. Okay. So draw the Lewis structure for the molecule. Oh, I'm assuming that the Lewis structure for this one is going to be, well, it could be just a simple line drawing, or it could be a dash wedge. I'm not sure what they're after. Which atoms are connected? Well, we've got 2 carbons, right? You got 2 carbons here for that molecule. And then it depends on which way you rotate it. If we rotate it like they did before and bring this one around, then this one will be in front. So this one's going to have a methyl and hydrogen here. And then on the back, you're going to have 3 hydrogens. Okay, let's see if I got even close. What? What atoms or groups are attached to each? Okay. That didn't even give us an answer. Okay, so there's your answer. Actually, it doesn't make any sense unless we look at it. If this one's going to be in front, is that the answer? No, that's the problem. Maybe I need to break out the model now. So if we make a dash wedge out of this, and this is in the plane, then this one's going to have to be dash. This one's going to have to be wedge. Okay. No, actually, these are all going to be wedge because they're coming out at you, and these are going back away. That doesn't make any sense. I think I need a model. Yeah. I think I need to put together a model on this one. So let's be sure I get a sp3 carbon there and there, and hook them together. Okay. Now I'm going to put 3 hydrogens on the back Hopefully we won't have to do this for every structure we're going to look at today. We just need a frame of reference here. Okay, so if I do that, those are in the back and this is in the front. All right, and that's staggered. And I need a methyl group here. I'm gonna leave the hydrogens off because it's gonna be too busy. So if I do that and I rotate this around, where I've got carbon and carbon like that. Okay, I've got this conformer, and then I rotate this around this way. This is in the plane. This is, nope, this is wedge. This one's a wedge, and this one's a dash. Okay, now on this side, this one's a wedge. This one's in the plane. It should be kind of opposite that one. That, and this one is a dash. Let's see. There ought to be an easy way to do that. Oh, by the way, if you go into Brightspace and look at the course, you'll see a section in there for this the exam module that has links to videos by a person by the name of Leah. You ever seen those? Yeah, they're good. She does brilliant explanations. If we have time, we'll look at one or two of them, but I would suggest that in order to ground yourself in the easiest way to get through drawing these models is to look at her videos. Oh yeah, they're excellent. In fact, I had to look at 2 or 3 of them this morning just to get my bearings. Okay. And 3-dimensional spatial recognition for me has always been difficult. And I think, don't get me wrong, I'm not gender biased, but I think there's sufficient clinical evidence that males do worse on spatial recognition than females. Well, if you go to the brain structure, right? Let's see, I forget the name of the connection between the 2 halves. There's a name for it. It's anatomical name. The connection between the 2 halves is much stronger for females than it is for males, unless the male starts heavy into music at a young age. Then the connection is established at a young age for males too. Okay, back to the topic. Enough anatomy for today. So if we look at the energy relationship between the different conformers, you find that for this very simple molecule, this is ethane, C2H6. So you've got 2 carbons and you got all the rest of the positions are occupied by hydrogens. In the eclipsed position, you have higher energy because you have the groups in the front and the back. The hydrogens in the front and the back are closest to each other. And for the same reason that we do VSEPR, the electron repulsion from the 2, particularly from their bonds, increases the amount of energy required to get them in that conformation. Then when they go into the eclipsed, that is more stable. It's lower energy. And it happens over and over, right, for this simple molecule. Now, if the percentage of the molecules that are in one or the other of these conformers depends on the amount of energy that's put into the system. And the easiest way to do that is to raise the temperature. If you raise the temperature, then you're going to have a significantly higher percentage of the conformers represented in the eclipsed conformer arrangement, because it takes more energy to get into that position. But these things are I like to think of them as whirligigs. They just spin all the time. But they don't like to be in that high energy situation. Now, this gets more complicated when you substitute different groups for those hydrogens. I don't think there's anything to be learned here. All right, what do they mean by torsional strain? You know what? You've had physics, right? Okay, you know what torsion is. It's a twist, right? And there was a time when there were some automobiles that were made, rather than the springs in their suspension, they were made with torsion bars. So the wheel would go up and put torsion, put a twist on a bar, and then when it came down, it would release. And they used torsion bars instead of springs.
Kind of like springs that they used to use on the carriage.
Now those are leaf springs. You've got coil springs. Most cars now have McPherson struts in the front, so they have the coil, and then inside the coil they have the shock absorber. It saves on space. Or some of the larger trucks will have leaf springs because they can be adjusted. You just put more leaves in there if you're going to have a heavier truck. But the torsion bar requires a little more engineering, and I think most manufacturers kind of gave up on that idea. But think of the torsion as a twist on that sigma bond around which the substituents are spinning. And the highest torsional strain is going to be found in the eclipsed position, simply because of the electron repulsion. Okay. Now we're going to get into a situation where the strain on that eclipsed position is going to increase significantly if you have a bulky group there rather than a hydrogen. But we're starting off simple with hydrogens to emphasize the electron repulsion. But once you get bulky groups in there, or you get electronegative things like halogens in there, then you increase the torsional strain significantly. All right. And we've seen the graph on the left already, but the one on the right emphasizes the percentage of conformers that are in the eclipsed position, depending on the energy required. Right? So when you get to, they must have measured this, 12 kilojoules per mole of thermal energy, you have about 2% of the molecules are in the eclipsed position. So if you increase the energy, you're going to increase that percentage also. This emphasizes there's a rotational energy barrier. Okay, now we're going to change one of those hydrogens to bromine in the front and bromine in the back. So two things are happening here. Bromine is more electronegative than hydrogen, right? So it's going to increase the density of electrons around the bromine, not just in the bond, but in the bromine. Plus, bromine is huge compared to hydrogen. So you get the bulk and the electron repulsion added to this molecule. Now, what that does is it changes the energy profile. So you still have the highest energy is in the eclipsed conformation. So depending on the angle of rotation, the very highest ones are going to be eclipsed. But now that you have you have bromine there instead of hydrogen, you can have bromines relative to each other in that eclipsed position, or you can have them in the anti position. And anti would put, let's see, anti would put, let's do this, like that, and then here, here, here. The anti would put bromines here. Right? So that bromine's in the back on the bottom, this bromine's in the front on the top. And these are hydrogens. That's the lowest energy. You've got those bromines as far away from each other as possible. Now there's another position where you can put the bromines. They move slightly closer to each other, like that. And, oh, excuse me. I didn't go far enough. This relieves some of the strain, the torsional strain, when you put them at 60 degrees instead of 0 degrees. This is called gauche. A. Right. I don't know if it came from the French, but I know gauche means to the left. And droite means to the right. Droite.
Yeah.
Trying to remember how do you, I think it's spelled this way. This is right. And this is left. So I guess if you're looking at it from the other direction, that's left. Or it means in something entirely different in chemistry. Is that even close?
Like anything.
Oh, yeah. Well, in the sciences, you actually, unless you're in the medical profession, the sciences tend toward Greek. Yeah. But in the medical profession, they like Latin for some reason.
I think 80% of all English come from French.
English?
Yeah,
Yeah.
like our core words, so like pig, dog, and so it's Germanic, so that's why I still consider Germanic language.
Yeah. Thanks to the Norman Conquest. William the Conqueror, 1066. He really messed our language up, didn't he? Okay, so this is known as gauche. This would be, and if it were over here, that'd be eclipsed. Down here, it would be staggered. Right? No. Oh, what am I thinking? Stop. Let me get this thing right. I'm talking to myself. Okay. Yeah, I was right. That's gauche. Yeah. There are actually 1, 2, 3, 4, 5. There's 6 people in this room. 7 people.
Oh.
Right. 4 students, me, myself, and I. So I can carry on a group conversation whenever.
John, you said stop.
Okay, so we have different eclipsed possibilities. The gauche does put these substituents at 60 degrees from one another. So that does relieve some of the strain of the eclipsed, but not a lot, not all of it. And then if you go back up to another eclipse to where the bromine is, let's see, that wouldn't be the right drawing. If we do, let's see, I want to be consistent with the way they're doing it. Yeah, they put this one in the front. And if we do this, left, 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 we do that, then you can have bromine here and hydrogen there. So we have a different eclipse here. Rather than the highest energy eclipse, we're eclipsing with bromines against hydrogens. And hydrogens against hydrogens. So that raises the energy level again. And then once you get to anti, that's the very lowest energy. And that's where most of the molecules are going to be, unless you raise the temperature significantly. All right. So anti-conformation puts the bulky groups at 180 degrees from each other, and gauche puts them at 60 degrees. How is this different one? It's not different, right? No. Substituents that are ghosts to each other contribute steric strain to the molecule. Well, yeah, there is steric strain. It's just less than the eclipsed. But there's still steric strain. These bromines are close enough to each other, or those molecules or those substituents are close enough to each other to introduce both torsional and steric strain. All right. Well, let's look at. Now that was just for 2 carbon molecules, which is the small minority of organic compounds. So when we take these long molecules, we're going to put them in a zigzag conformation. And the reason for that is that it's more realistic, right? Instead of writing the carbons in a string and doing that, which is valid under some circumstances, but to get closer to reality, zigzag is a better way to do it. So that's why you've been seeing structures written as zigzags, and I hadn't heard any protests. So I figure that it's sinking in. And that has to do with the sp3 hybridization to get the zigzags in there. Now, when would we not have a zigzag in a molecule? When you have pi bonds. Yeah, pi bonds straighten things out, at least for those 2 carbons. Or actually, you can get 3 carbons with 2 pi, with pi's on either side. Okay. So now we're going to talk a little bit about 5 and 6 membered, actually, and less rings, and how stable are they? Right? How can we approach them in terms of conformations? Let's see. It's still up in the way. Is there anything hiding behind there? No, there's not. Okay. These are just examples of 6-membered rings, 5-membered rings. So you can have simple 6 and 5-membered rings like the first one and the last 2, or you can have combinations. Diamond, in fact, is a single molecule. Androsterone is one of the steroids, and they all have that fused ring arrangement where you have 3 6-membered rings and 1 5-membered ring, and all of the sex hormones, all the steroids are based upon that structure. Okay, Let's talk about ring strain. Which one has the least ring strain? Well, if we look at that table on the right, we find that cyclohexane has 0 ring strain. And we're gonna draw it in a few minutes and see why that is. But if you deviate from that 6-membered ring in any way, you start to get ring strain, and the 3-dimensional structure of the molecule at minimum energy is going to try to reduce that ring strain as much as possible. Now, these compounds do exist, right? Cyclopropane, cyclobutane, pentane, hexane, heptane. They do exist, but getting them, producing them in a chemical reaction can be tricky. You can have torsional strain, you can have steric strain, just depending on the factors that we've discussed earlier. You also get an angle strain, right? For an sp3 hybridized carbon, what's the angle? Under 9.5 degrees. Right? For any carbon in sp3 hybridization is 109.5. So the closer you can get the bond angles in that ring to 109.5, the less strain, the less angle strain there will be. And cyclohexane is a good example of that. It's not exactly 109.5, but it's very close. So much so that the ring strain is essentially 0. Okay. If we look at these molecules, which one would have the least ring strain? I think B. B would have the least ring strain. And then what would be the next? A. And then the next would be D. And the greatest ring strain would be C. So B, A, D, C should be the order. Angle strain, particularly angle strain for these ring structures. All right. So why does cyclohexane, and that's what that simple arrangement there is, cyclohexane, right? But that's not the 3-dimensional structure. What we need is a way to represent that structure so we see something that's closely akin to reality. And that's where, that one, that's where the chair conformation comes in. If this 6-membered ring is represented by what looks like a chair, it looks like a lawn chair. That's why we call it the chair. Then the angle strain is very close to, let's see, we're going to have, right, each one of these, since they're single bonds, each one is going to have hydrogens. But we need to do 2 things. We need to change the angles here so that we get very close to 109.5. What did they say it was? 111? 111. For pure cyclohexane. And the way it does that is to alter the arrangement of the carbons and the hydrogens around them so that we minimize both steric strain, electron repulsion, and angle strain. If we look at this, okay, that last one on the right, is a Newman projection of this molecule. And in order to do that, what we have to do is say, okay, we've got to take two of those bonds and put those in and look down the axis for those two. And if we do that, then notice that we get in the front, we get a carbon and its hydrogens up here. And in the back, we get a carbon and hydrogens down there. And that looks like, if we take that, let's see, if I draw, see, I'm going to draw it like this. And then I'm going to put here, that. That's not quite right. Put it down here. That connect. So there's my chair. And if we look down these axes, then we see this carbon up here and this carbon down there. That's how cyclohexane minimizes strain. If we go to cyclopentane, the options are not, it doesn't have the options that cyclohexane does. So we get what's called an envelope. We do get some pucker on one end, but the other end is locked in place. So you get much more strain, angle strain in those bonds. That tells me when you have excess strain in a molecule, these ring structures should be more amenable to breaking bonds, reacting and breaking those bonds because there's more strain. If we go to a four-membered ring, cyclobutane, we get exceedingly higher strain. And we get some pucker, but there's not much available. Right? If we look at the Newman projection, we can only look down one of the bonds. The others, we cannot do a Newman projection on more than one sigma bond. Whereas, well, same thing for the cyclopentane. We can only look down one of the bonds, and the others have to just we have to draw those where they best fit. Okay, and then cyclopropane, this one is going to be extremely reactive, I think. The bond strain here is going to be enormous because the bond angle here is 60 degrees. That's a long way from 109.5. There's enormous strain here. So you'll find that in some of the reactions we study in the future, we're going to find that these three-membered rings are very reactive. All right. All right. If you've ever wondered how these ring strains have been calculated, we calculate them from the heats of combustion. In other words, the amount of energy given off by the combustion of these, remember what a combustion reaction is, right? You always have to have oxygen as one of the reactants. So in this case, we've got hydrocarbons. So if you ring structures, that's a good, they didn't make that point earlier, but ring structures can be written like this, CH2 to the N. Right. So if we have 6 here, that would be 6 carbons and 12 hydrogens. So we got 6 carbons and 2 at each one, so that's 12 hydrogens. Right. What if we have a 5 here? Right? 5 there would be 5 carbons and times 2 would be 10 hydrogens. Right, so that's right. If we have a 4 there, then we'd only have 8 hydrogens. Right? 2, 4, 6, 8. If we have 3 here, then we'd only have 6. Right? 3, 6. So this is the general formula for an aliphatic ring. CH2 with a subscript of N. If we react any one of those with oxygen, then we know it's going to require N times 3/2 of the oxygen. And then if we come in and divide the heat by N, we can get a value for energy per carbon. Okay. So the enthalpy based upon the carbon will change depending on whether it's a 6, 5, 4, 3 membered ring. Okay. So if we look at this first one, we do the calculations and we find out that the strain per carbon is 0. Well, we're going to call that the reference. Excuse me. This is going to be our reference. So 615.1 kilojoules per mole is our reference. Then if we do the calculation for cyclopentane, we get 620. And the difference there is 5.4 kilojoules. So the strain there is 5.4 kilojoules per mole of carbon, or if we have 5 carbons, then it's 27 kilojoules per mole. That's where those values come from. And I guess that was just to illustrate the calculation. You can do the same thing for the cyclobutane and cyclopropane. Okay. This might be a good time to produce a 6-membered ring. Be sure I got sp3 carbons in here. And you'll notice as you try to make the last connection, okay, how many is that? 1, 2, 3, 4, 5. Right. Put my last carbon in here. I've got the right kind. And when you put the last carbon in there, you're going to notice that it's difficult. It's difficult to put these carbons in a flat plane. What they really want to do is one's up and one's down. So I think we're going to need the rest of these. I knew that was going to happen. You know what I did? I put an sp2 hybrid carbon in here. P3. Let me be sure I got the rest of them. Nope, there's another one snuck in there. Won't work. Okay, that one's good. That one's good. That one's good. Oops, that's a 5-member ring. I need another carbon. Now we're talking. Okay. Now let's put the rest of them in here to get our hydrogens in place. I'm not going to put any white balls on here unless I have to. Let's see. I'm sorry. Green? You got a green?
No. Moving.
Oh, I um. They're giving you a color code for axial positions versus equatorial positions. Axial positions are like up and down, and equatorials are like side to side. Now they're not exact. They're huh? Yeah, that's just to illustrate the. Okay, if we put it in this chair conformation, all right. So I've got these bonds here. This one in the back, and this one are lined up. So we could turn it like that and look Newman projection down here and here. But in the chair conformation, we've got some of them that are definitely pointed up, up here, and down, down there. All right. But the equatorial positions, oops, run away. The equatorial positions can look like they're slightly below the plane or slightly above the plane. All right, in this chair conformation, like that. That's just definitional. The axials are always perpendicular to the plane. The equatorials are close to the plane through the molecule. Okay. Definitions out of the way. Now the molecule itself can have different conformations. In other words, it can rotate to a limited extent around these sigma bonds. And in order to do that, it goes through a what's called a chair flip. In other words, this one's up and this one's down on this side. They can go through and move into a boat conformation like that, and then the other one flips up and becomes the up carbon. All right, so we flipped from this side up to this side up now. And that requires some energy. So when you hear chair flip, that's what they're talking about. And this is the energy distribution when the molecule goes through. The half chair is the highest. So if we try to flatten this out like that, that puts a lot of torsional strain on those bonds right there. This is the half chair. And the boat, for some reason, actually it decreases, it brings the angle back into close approximation to the ideal SP3. All right, so that's a mid-level energy. And it can also twist. So we're going through half chair is the highest energy place. The chair conformation is the lowest energy. The boat is intermediate, intermediate high. Half chairs are extra high. And then this twisted boat is an intermediate low position in the energy diagram. But this happens, I mean, we visualize this, but it happens, like that in a split second. It'll go through all these conformations. Now, one of the reasons that the boat conformation is more stable than, say, the half chair is because when we look at the well, let's see, the half chair would be like this. there, like that. If we look at the Newman projection, we find that the okay, that first one is actually a boat conformation. So let's stick with the diagram. If we put it in the boat like that. Now, if we look down the axes, we get these hydrogens are closer to each other. They call them flagpoles. And they tend to, let's see. Okay, B has been twisted. I mean, it's been rotated. Yeah, B has been rotated to show down these two bonds. And what we're doing is we're putting the hydrogens in eclipse conformation, which increases the energy. Okay. Drawing. What's her name? Leah. Leah has a very good video on how to draw these chair conformations and chair flips. Yeah, you look at that one. Actually, how much time do we have? I'm going to run out of time if I'm not careful. I don't want to eat up your lab time. So look at her video. And there are a couple of ways to do this. She's got a very good way to do it. But one way I check to be sure that I'm doing it correctly, you draw two parallel lines like this, offset one another. And then you position, actually, I want to put my up over on the right. So let's do it this way. Let's see, about like this. Two parallel lines. And then you draw a dot up here about like that. Let's see. About like that. And then over here about like that. And then you connect the dots. It doesn't have to be pretty, but you need to be able to show the angles. Right? That needs to come down some more. Like this. That. And what I want to see is these two are parallel, these two are parallel, and these two are parallel. That gives you a chair conformation. And then you decide, just take one of either the up or the down, and you draw there, because we got to put our substituents around it. Maybe hydrogens, maybe something else. And then you just go around it. Like this is up, down, up, down, up, down. Okay. And then you take then this one's up, so this one has to be down. Don't draw it out like that. Don't draw it parallel to this bond. It has to be like that. So if this is up, that's down. Right? So that's down, this is up. That makes this down, and this up. And this is down, and this is up. Yeah. So there we have our positions for substituents. And from that point, okay, the dash wedge is trying to show us. I didn't draw that very well, did I? But you just have to turn your brain off. Now they've got drawing programs that do it really nice. You can draw those parallel lines like that, or what they did was they drew them like this. That. And then they put this one out here like this. And this one over here like this. What we're showing, well, let's see. I'm not sure how deep I want to go into Cardy's explanation here. These are axial. The up, down, up, down, up, down. These are all axial here. Axial, 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 axial. 1, 2, 3, 4, 5, and 6. Those are axials. These are equatorials. All right, so this one's going to be, that one's equatorial, this one's equatorial, E, 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 E. Um, so you should have 6 of each, obviously. This gives you a procedure for drawing them. If it was me, this isn't very much help. I'd watch Leah's oops. That made a whole lot more sense than it did when I tried to explain it.
Yeah.
So now we got drawing, we got chair flips, monosubstitution and steric strain. Notice for this cyclohexane, one of those hydrogens has been substituted with a methyl group, and that is very bulky. So bulky groups tend to favor the equatorial position because that puts them out further out into space, away from the other parts of the molecule, and reduces the strain on the molecule. That's just a rule of thumb, right? Bulky groups go equatorial, preferably. So if you find it in an axial position, just chair flip it to the equatorial. I think this is not going to help a whole lot. If you apply Leah's method to this one, you're going to come out okay. Notice, actually, if you notice on carbon 1, you've got the methyl group. And if we chair flip it to put that carbon down rather than up where it's attached, then you look at the right-hand plate, you'll see that now the methyl group is still up, but instead of being up axial, it's up equatorial, right? Because that hydrogen is still down, the other hydrogen that's attached to it. All right. So here's the effect of These are just hard numbers for the effect of the steric strain from a bulky group on chair flipping, and you find that the percent, depending on the group, right? If it's just hydrogen, you're going to have a 50-50 distribution of axial versus equatorial. But if we just put hydroxyl in there, you're going to find that you're up to over 80% in the equatorial. The amine group, over 90%. The methyl group, over 90%. The ethyl groups, over 90%. What's that next to the last one? It's an isopropyl group. Notice there are 3 carbons, which is propane, and then you're attaching on the middle, the second carbon. So that's what we call an isopropyl group. You're still over 90%, and the last one is what? That's a tertiary butyl group. Notice that there are 4 carbons. We're attaching to 1 carbon, and all the other hydrogen positions are taken by methyl groups. That is extremely bulky, and you find that almost all of the conformer is equatorial. So that's the effect that bulky groups have on the different conformations of cyclohexane. All right. So the next one is the Haworth projection. This is a very popular projection for the term just went right out of my head. Biochemistry and sugars. Right. Sugar representations are more often than not going to be given to you as Haworth projections. Now here's where we can reintroduce the concept of cis versus trans relationship, and it's probably best done with a picture. So if we look at this example, where we just draw the simple line, the dash wedge, and we represent the cyclohexane, the ring, in a plane, although we know it's not in a plane, but we're saying that the X and the Y are either facing us, coming out at us, or one of them is going in and the other one's coming out. So if that's the case, then we're going to say that the ones that are both coming out are cis to each other. And the one where X goes in and Y comes out, they're trans. If we take that molecule and just lay it over on its side, just push it back, push the top back, then the X and the Y stick up on the left hand, the cis conformation. And on the right, the Y points up and the X points down. So we're not too concerned with the Haworth projection in the ring itself, because we're saying the ring is in a plane, and we know it's not. Right? The ring is actually 3-dimensional. It's either a chair or it's a boat or something in between. But for the Haworth, we're more interested in the substituent relations to one another. And notice that the front side of that 6-membered ring is thickened like a wedge. That's showing that it's in front, it's coming out. So how are they related to one another? There's another, I don't know if I have that one linked. another Leah video on Haworth's relationship to chair confirmations. And that would probably be good. If we had time, I'd show it, but I don't think we have time to do that. So let's see if we can make sense of this one. If we take the Haworth and say that these methyl groups are in a cis conformation to one another on the 1 and the 3 carbons, and then we take the chair and we try to put those into the chair, where does it go? Well, as it turns out, when the Haworth cis up is equatorial, and the so for the, let's not do the chair flip yet. If we, well, it can either be equatorial, excuse me. It can either be equatorial. If they're cis, they're on the same side of the molecule. And notice that both methyl groups in either of the chair flips are pointing up. So that's important because the Haworth says they're pointing up. So each one of the chair and its flip should put them up. And they're still up whether they're equatorial or axial. Actually, the equatorial position is going to be the favored one. So if they find themselves in the axial position, they're going to flip to the equatorial. Now, if they're trans to one another, then there's no preference to one because one's equatorial and one's axial in one chair flip, and we flip to the other one. Now we've got one axial and one equatorial. So they're equally as interfering with one another in either position. So you're going to find an even distribution of either one for the trans conformations. All right. This is simply what the model would look like. And it's trying to show you in the trans conformation. The trans conformation will give you either chair flip will give you the desirable positions. One axial, one equatorial. All right. How do we identify constitutional isomers? It's simply the connectivity. Right? All you have to do is, if you're given two molecules, just say, are they connected the same? And that's going to be the trick. For instance, if you look at the two top ones, of course, those are obvious. One's ring and the other one's not, and they're the same. Right, cyclobutane. What would its formula be? It'd be C4, right? 2, 4, 6, 8, and H8. And but1-ene, right, would be like that. It'd be 1, 2, 3, 4, C4. Then this one would have 2, 4, and 6. Excuse me. No, 1, 2. This would be 1, 2, 3, 4. So that'd be 4. Excuse me. That's not right. 2 hydrogens here, 1 there. So 2, 3, and 2 is 5, 3 is 8, H8. So we got the same number of hydrogens, but it's obviously a different connectivity. Right, that's easy. But when we draw something like the bottom one, when we put 1, 2, 3, 4, 5, 6 in a row, 2, 3, 4, 5, 6 in a row, and then we branch off of the 3 and the 5, right? Then is that different from the one where we draw 1, 2, 3, 4, 5, 3, 5, And then we do a branch like this, like that, and one like this. Is that different connectivity? Well, what's the longest one here? It's obviously 1, 2, 3, 4, 5, 6. Okay. What's the longest one here? 1, 2, 3, 4, 5 would be that. 1, 2, 3, 4, 5, 6 would be this one. Okay. And we have a methyl group off of the 3 and the 5 here. And did I draw that right? Oh, I'd have to draw it back the other direction. If I drew it back this way, 1, 2, let's do it that way. Otherwise, I can't make my point. 1, 2, 3, 4, 5, 6. So this one has a methyl group off of the 2, off of the, 3, off the 3, and off the 5. So these two molecules are exactly the same, right? They are not isomers. They're the same molecule. They just look different. So that's where you can get tripped up. Is how they're drawn. All right, these are rules. I'm just going to leave it up there long enough to get recorded. And there we go. All right, they're drawn from that side. 1, 2. If I drew this one from this side, 1, 2. Oh, this would be preferable because that would give 2. Yes, yes. I drew it backwards. Okay, here's another concept that's important to remember and learn how to use. It's the index of hydrogen or degree of unsaturation. Index of hydrogen what's the D stand for? Deficiency. Thank you. So that's index of hydrogen deficiency. Okay. This is very useful when you're trying to deduce the structure from the molecular formula. So in short, this index of hydrogen deficiency is just a comparison of what would a saturated molecule look like. How many hydrogens would a fully saturated molecule look like, or a non-ring structured molecule, right? So if you had 6 carbons, right, you would have a maximum of 14 hydrogens, right? Yeah, 3 on the ends and 2 for each one in between. But if we actually came up with, if we had a structure that was H12, that means we're missing 2 hydrogens, and you probably got a double bond in there, right? So if you drew something like this, and you had 2 hydrogens here, 2 hydrogens there, you took one of those away, one of those away, there's your double bond. Okay, so that's where we're headed with this index of hydrogen deficiency. Here's, all right, for this example, we're actually using the structure and determining the index of hydrogen deficiency, but I think you can do it from the formula as well. So we're going one direction this way, we're going to go back the other direction subsequent to this. So these are the rules. Each double bond contributes 1 to a molecule's IHD. So if you have a double bond, then your IHD has 1 value added to it. Triple bonds have 2. A ring contributes 1. Why? Because if you look at it this way, if you have hexane, 1, 2, 3, 4, 5, 6, then what happens if you've got 3 hydrogens out here and 3 hydrogens out here on the end, and it whips around and grabs its own tail, right? And makes a bond with that. In order to make that bond, you got to get rid of that hydrogen and that hydrogen. So the index of hydrogen deficiency, then we add 1 for the ring. So we lose 2 hydrogens, the deficiency is 1. Okay, so examples, right? We've got 1, 2, 3, 4 pi bonds, right? Each pi bond, each double bond gives you 1 hydrogen deficiency and 1 for the ring, which makes the index of 5 for that first molecule. If you have 2 pi bonds, then you got 2 for each one of those triple bonds, and then 1 for the double bond. So you have 5 there for each one of those, right? 2 plus 1 plus 2. And then for the last one, what do you do with fused rings? Well, let's see. We got 2 pi bonds, so that's 2, and we got 3 rings. So the total is 5. And the rings don't have to be all carbons, right? That middle ring is abridged with oxygen. Okay, now we got to learn what to do with those values. Well, if you're going to draw a constitutional isomer of a molecule, in other words, you're going to draw from the same formula, you're going to draw 2 or more structures. And you want to know, this is actually a check on whether you're doing it right. If you calculate the index of hydrogen deficiency for one, and it's not the same as the IHD for the other one, then you've not drawn the correct constitutional isomer. So for this A, we have ethane. And we make 1 bond out of between the carbons. Now we're deficient by 1. If we make another bond in that middle, then we're deficient by 2. Right, we don't, each one of those, ethane, ethene, and ethine, they're not constitutional isomers. Right, because they don't have the same formulas, for one thing. And for the other, they don't have the same index of hydrogen deficiency. The last one, if we take ethanol, right, it has an IHD of 0. Well, if we make 1 ring out of it, then its IHD is 1, and that's oxirane is not a constitutional isomer of ethanol because it has a different IHD. So what's the IHD for naphthalene? Well, let's see. We have 1, 2, 3, 4, 5 double bonds. That's 5 plus what? 2 rings. So the IHD should be 7. Okay. Okay. Suppose we have a formula. Now we're going to go back the other direction. We were looking at structures and calculating the IHD. So what we want is the IHD to help us to determine the most likely structures, or 2 or more potential structures, constitutional isomers for the same formula. And I gave you that one before. For all alkanes, this is going to be, I do it like this, 2 times n plus 1. And the author likes 2n plus 2. It's easier for me to calculate. They're the same thing. You factor out the 2, right? Okay. So this is going to be a fully saturated molecule. And we work from there backwards. The presence of oxygen has no effect on the number of hydrogen atoms. Okay. Presence of nitrogen increases the hydrogens by 1. So if we do have a nitrogen in there, we have to add 1 to it. So the number of hydrogen atoms is 2n plus 2 for the number of carbons. And then however many nitrogens you have adds another hydrogen. And then for every halogen, we subtract a hydrogen. And the illustration is there is trying to show you why. The oxygen only has 1 hydrogen to begin with because it can only have 2 bonds, typically. Nitrogen has an extra hydrogen. 1's accounted for in the structure of the molecule itself. And then fluorines don't have any hydrogens. Halogens don't have any hydrogens, so we have to subtract 1. So that's another rule. When you start to calculate, you have to find oxygens, nitrogens, and fluorines. Now, what do we do if it's a sulfur? I'm thinking sulfur's in the same group as oxygen. So it's going to do the same thing as oxygen, have no effect. Right? What about nitrogen? Nitrogen has phosphorus. If phosphorus is in there, it should increase the number by 1. Well, halogens are off by themselves. They're all the same. Okay. So let's see if we can calculate the IHD for this molecule. Let's see. C7H8. C7H8. NO2Cl3. NO2Cl3. Okay. All right. So we have carbon will be hold on a second. Yeah. This would be 16 for the carbon. And nitrogens add 1, right? Oxygens add nothing. Chlorines are -3. So it should be 14, right? If I did that right. I didn't do it right. What did I do wrong? For given, so the saturated hydrocarbon would have, the saturated would be 16, and we're deficient by 8. Right? So that's actually 8 plus 1 minus 3. I did something wrong. Let's figure it out. In carbon atoms, saturated would be N equals 7 would be 16. Okay, got that far. Oxygen atoms don't change the number. Nitrogen increases the number by 1. So I got those. Nitrogen increases by 1. Okay. Number of in the saturated would be 14. -3 would be 14. Okay, so this would be saturated. Okay. I left out a step in the procedure, didn't I? We only have 8. Right? So since we only have 8, we're deficient by 6. Right? 6 fewer than in the 14. The IHD is half the number of missing hydrogen atoms. Okay, I missed that step. Did you see it and I just walked past it? No? We all missed it, right? Okay. So that's 6 divided by 2. So the index is 3. Maybe that was written back here and I just number of hydrogen atoms in a saturated molecule. Okay. Well, I think they missed telling us about it. Well, they told us now. So how do we use this? Well, we take the formula and we determine the IHD from the formula. And then we draw possible backbones. Leave out the double bonds, triple bonds, halogen atoms, add those later. Include rings. The number of rings must not exceed the IHD computed from step 1. Each structure, however many, contain fewer rings than the IHD. So the maximum number of rings we can have here is 3. But if we have 3 rings, we can't have any double bonds. We can't have any pi bonds of any kind. And the addition of the nitrogen and the chlorine have to be taken into account also. So this is a case where you draw every possible structure. Then we add the halogens for step 4. All right, for this example, we've only got fluorines. All right. So all constitutional isomers of C4H8F2. So what's the IHD for that one? Is that right? IHD equals 0? If we have C4H8, C4H8F2, right? 2. Okay. Saturated, it would be 10. All right, 10 hydrogens. But we've got yeah, I'm working from the formula. Yeah, I'm working from the formula. So this is the total number of hydrogens if it were saturated. Okay. We actually have 8 hydrogens. Right? So we're deficient by 2. Well, we're deficient here by 2. That's equal to 0 divided by 2 is 0. So the IHD is 0. So what would be all the possible, we're not going to have any double bonds. We're not going to have any rings, right? Because the IHD is 0. So it has to be a linear or branch structure. So what's possible there? Well, if we put 4 carbons in a row, like that, or we could put 3 carbons and then branch it. That'll be 1, 2, 3, 4. There's 4. Yep. No rings. All right. So now we got to put the fluorines in. So where can they go so that we have unique connectivity? Well, we've got 2 fluorines. We could put 1 fluorine on this 1 carbon, right? Or we could put a fluorine and put the second one there. That's one possibility. We could put, let's see. We could still put a fluorine on the end. If we put a fluorine over here, is that going to be unique? Yeah. Right, this is 1, 2, 3, 4. Okay, 1, 2, 3, 4. If we put a fluorine on this one, that would be different. Or 1, 2, 3, 4. If we put a fluorine on this end and a fluorine on this end, right, that would be different. What if we put a fluorine here and a fluorine here? How about that? Or if we put 2 fluorines here, like that. Now, what if we put 2 fluorines over here? That'd be the same as this molecule, because you just flip it around, exactly the same. Or if we put 2 fluorines out here, flip it, be the same. Right? So these are possibilities for the straight chain structure. Let's see. So did I get them all? 1, 2, 3, 4 for the straight chains. Ooh, I got 5. So their G is this one, right? H is 1 and 2. 1 and 2. I is 1 and 3. 1 and 3. There we go. And J is both ends. Okay. How about this one? Oh, L. L. That one. Yep. And M. I missed that one. On 2 and 3. Yep, I left that one out. This one and that one. Those are all possibles for the straight chain. Okay. How about the branch chain? I'm not going to go through all those. We don't have time for it. But you just have to use your imagination, and it's probably easiest just to bulldog your way through it. Think of any combination possible once you've got the backbone, and then eliminate the ones that are duplicates. I think that's what the author is doing here. Yeah, think in 3 dimensions, right? If you go this way or this way, right? Does it look like any of the others? Yeah, yeah. But the calculation of the IHD is the first skill. Once you know the IHD, then you know how the structure is limited. Okay, this molecule, they say, has an IHD of 1. Is that true? C3H6. C3H6O. And so we have possible 8. 8 hydrogens would be saturated, but we've only got 6. And oxygen doesn't contribute anything, so divided by 2 equals 1. But IHD is 1. So it's possible it could have a ring. It could have a 3-carbon ring, like A. It could have a heterocyclic ring, a three-membered ring, or it could have a 4-membered ring. Any one of those works. Or could it contain no rings and be IHD 1? Not without a double bond, right? D, E, and F would have 3 carbons each, but there has to be a double bond in there somewhere. Is that what they're going to? Yeah, they're doing that on the next slide. So you got to put 1 double bond in there somewhere. So we're doing the backbone first. right? These are all the possible backbones with the oxygens included. And then you throw a double bond into D, wherever it will go, E, and F. All right. So I think that's going to take a lot of practice. In fact, I could use some more practice too. Leucine and isoleucine, these are amino acids, right? If you're going into biochemistry, you'll see these again. And depending on whose course you take, you'll probably have to memorize them. If you take them with me, I'm not so picky about memorizing them, but what is it, 20 of them? Yeah, 20. There's a logic to them, right? So you can reduce some of the load. Yeah. Okay. The sugars, the monosaccharides, they have massive numbers of constitutional isomers. And the tricky thing with sugars is that they have both straight chain and ring structures. These are called, I think they're called hemiacetals, right? We may get into that later. But the either the head grabs the tail and makes a ring, or sometimes the head grabs the second carbon and makes a ring. But they flip back and forth between those two. So this is the for monosaccharides. You can have usually two versions. If you look for the carbonyl group, because monosaccharides all have hydroxyls, bunches of hydroxyls, but one carbonyl. So that double bonded O can either go on the end of the molecule or it can go on the second carbon. If it goes on the end, you're going to make the ring structure is, well, actually it's an aldose. It's like a aldehyde. Like aldehyde. So we add whenever you see an OSE on the end of a word, think sugar. Or a ketose. If it's on the second carbon, then you've got a sugar that's a ketose. Glucose is an aldose, fructose is a ketose. They're both six carbon structures. And everybody knows, well, maybe not everybody, but if you hook glucose and fructose together, what do you get? Table sugar, sucrose. Yeah. Okay. Saturation and unsaturation. I'm not going to go into a lot of detail here. It's just to illustrate that saturation means no double bonds, no triple bonds between the carbons. And for fatty acids, you're going to have a carboxylic acid on the end. And if it's unsaturated, you're going to have 1, 2, sometimes 3, usually, double bonds. And they're not going to be conjugated. Remember, a conjugated, if we do like this, like that, and we put a double bond here and double with a single in between, those are conjugated. So they can resonate and stabilize. But unsaturated fatty acids usually put one here and then skip 2, put one there. And they have names. Oleic acid, linoleic, linolenic. These are the desirables. to put in your diet. All right. So what happens with, now we're going to talk about what happens when you put a double bond in an aliphatic chain. It essentially puts a kink in it. And remember, these long chains, what type of interaction can they have? Well, let's set the carboxylic acid aside for a moment, because that would be a dipole, ion dipole interaction if you try to put them in solution. Or if you had simply the pure substance, then how is it going to interact with its neighbors? What effect will it have on the melting point? If you have a long straight chain, the London dispersion forces are there in force. The longer the molecule, the more attraction you have from one to the other, so the melting point will go up. So the longer the chain, the higher the melting point. But if you put a kink in it, now they can't lay side by side easily, and that decreases the melting point. So unsaturated fatty acids in food stocks have lower melting point. And that's why, for the longest time, restaurants wanted saturated fatty acids, because they put them in their fryer, and they need a high melting point, which also translates to a high smoke point. So they can heat it up to a certain temperature and it won't degrade. But if it's got a lot of double bonds in there, it's going to have a low melting point, and the higher temperature is going to degrade your oil. Oops. Okay, so that's the end of that chapter.